Okay, so now we are ready to look at module number 3. Module number 3, we're going to still be in chapter 2, but we're looking at different sections. So let's go into our learning plan for module 3. So you'll notice here that we're going to be skipping over to section 2-3. We're going to be looking at forces and equilibrium in a plane. So equilibrium of a particle, all that means is that it's equilibrium of concurrent force systems. They share that common point, okay? We're going to be looking at free body diagrams and drawing those appropriately. And then the problems that are going to be included in your practice problems are going to be the example or the sample problems that we see here. 2.4, 2.5, and 2.6. We're going to be solving all of these using the rectangular component method. Even though they're going to be solving them differently in the samples, your requirements are the rectangular component method. Okay, so that's why it's important. Make sure that you follow along and write it out the way we have here. If you follow the way that they do it, they will get the same answer, and it is a valid way of doing it. But I want the practice on the rectangular component method. And then as far as what you'll be submitting, you have a Connect assignment associated with the concepts here. And then you're going to have the practice problems to hand in, which we'll be working on tonight. And then application problems are going to be the ones that are like your assigned work. Okay. So, and then that'll be the assignment probably number 3 or the application problems for module 3. All right. So let's go underneath our camera and look at where we're starting in the chapter here. So for section 2.3 here, forces and equilibrium in a plane. So you guys have all had physics at this point, right? You've all had math. Equilibrium, what does that mean to you? Forces are balanced out, absolutely. What else? Does it mean anything else? Yes, the resultant force equals 0. Absolutely. Yep. Anything else? If I'm in equilibrium, am I moving? Can I be moving? I can be. There's dynamic equilibrium, right? And what else? Static equilibrium. Static equilibrium, statics class, is that we're not moving. So that is our assumption all the time in this class. That's why we're called what we are, statics. Technical statics is we're not moving. You will have a class later on, it's called dynamics. And then you're going to continue kind of the conversation, if you would, and you're going to be continuing and looking at the effects of forces and the applications to mechanical engineering when things are moving. But in statics, we're not moving, okay? And we're in equilibrium. That's the other condition. So we're static equilibrium. Now, just kind of going back to physics, when you're in dynamic equilibrium, what would be a common condition or a common application of dynamic equilibrium? Do you remember? Are you accelerating when you're in dynamic equilibrium? No, that's when you have a constant velocity, okay? So sometimes students forget that you can have dynamic equilibrium. It doesn't just have to be that you always are at rest if you're in equilibrium. No. It's just that everything equals 0. It's a condition of equilibrium. Everything equals 0, and we happen to not be moving, okay? But you can have that same, all the forces balance out and equal 0, and we can be moving at a constant velocity, right? Constant velocity. Okay, cool. So equilibrium. Now, when we are in static equilibrium, again, in this particular section, we are keeping it to, concurrent force systems. So our forces are all going to have a common point of application. Okay, so we'll see arrangements just like this. Now, as mentioned earlier, the resultants are all going to equal 0. And because we're dealing with forces, that means that we're dealing with vectors. So we're going to sum those vectors to equal 0. And we're going to, anything that is not on the X or Y axis, we're going to resolve into their components, and we're going to add and subtract in those X and Y directions to help us with this process. Okay, so we're going to be using the rectangular component method only. All right, so we're not going to add forces like this. You can, but then I'd have you pulling up AutoCAD and drawing everything to scale and all that kind of stuff. And as much as we love to do that, we're going to practice the rectangular component method. Okay. Now, as I turn the page here, you're going to notice that two equations of equilibrium are going to be what we use. The first one is going to be, we're going to sum the forces in the x direction. They're going to equal 0. Okay. That means that when I get everything resolved along that x-axis, here's my condition. I'm going to set it all equal to 0. Same thing for the y-axis. Sum the forces in the y equals 0. This is my second equation of equilibrium. So when I look at everything on that y-axis, I'm gonna say, okay, all of them have to balance and equal 0. Okay, that's a condition. So I'm not solving anymore any resultants. I'm usually going to solve for unknown forces using the condition of equilibrium. Okay. So, and then the next section here, statics truly is an application, or it's not really a branch, but it's like we're using physics in almost everything that we do in statics. Okay. At the other college that I was at, I believe you guys in your sequence of classes, you take physics before statics. Is that right? Most of you, or you don't have to? Okay.
I think we take physics next year.
Oh, you take physics next year. What I find interesting is, well, at the college that I was at, we took them actually concurrently, my old college. And I would have students that would kind of hold off on stat or on physics before they would take statics. And you might find this later on, not that it's a bad thing, but a lot of students were like, oh, I now understand more about statics because of the physics I had. Most likely, most of you have had physics along the way, maybe not formally at, WCTC in your degree, but you probably had it in high school and stuff like that. So this stuff sounds familiar, but truly when you take physics later on, you're gonna be like, oh yeah, this all makes, not that it doesn't make sense now, but you're gonna see it again. You're gonna see some of these things again. And Newton's law is one of them. Okay. So Newton's first law, it says that the resultant force acting on a particle is going to be 0 unless it's acted on by an outside body or an outside force. Okay. So, so that it's just saying that that's an application here, and we're going to continue to reinforce that as we go along. Okay. Not formally, I'm not going to always say, oh, this is Newton's first law, but it is an application of. The next part that they're going to talk about here is going to be something that we're going to continue to do and refine all the way along. So, free body diagrams and creating them. We've been just kind of calling them right at the moment diagrams, but free body diagrams is like the formal way of, saying it. And what that means is that we're not going to worry about the details of what the elements are. So we saw, forces that were coming off of hooks. You don't have to draw the hook. We're just going to draw an XY axis, show where the origin is, and we're going to draw the forces simplified off of there. So free body diagrams are simplified versions of what's actually, going on. And then making sure that you have all of the information in the format you need it to be. So if it's a force, it has to be aligned with a vector. If it's a force, we also have to have an angle or solve for the angle to fully define it, and making sure that all of our labels are there. As we go along and we continue to add on to this subject, there'll be standard ways that we show certain things like pin reactions or roller reactions or cantilever beams. And those will come a little bit later, but right now, free body diagrams we'll get an introduction to. So for instance, you'll notice that we have in figure 1224, we have a package or some sort of a cargo that is being lifted with a cable, and we have two cables going up to B and C that are all connected at point A. All right. And a very common problem in statics is, okay, if this has, a weight of 2,000 pounds, okay, what is the force in each one of those cables? What is the tension in each one of those cables? And I would want to know that because I would, first of all, want to make sure that if I'm going over and I'm actually pulling, that the person who's pulling can, lift that or pull with that force. But secondly, I would want to know if whatever the size of the cable was there could actually take a tension force in whatever it is, because I don't want it to break. So I'm going to have to have, some sort of a limit on the amount of force that I can put in there. And that's going to help me determine that. Okay. Have you ever, you know, been in an elevator where it says capacity is like, I don't know, 2,000 pounds or 1,000 pounds or whatever? And have you ever been in an elevator where you packed a whole bunch of people in there and you're like, I'm thinking we've exceeded that. When I was in college, we used to do that all the time. You'd get up, you know, you'd go up to whatever floor you were going to go in. Nobody wanted to wait for the next elevator. So you would just pack people in there. And as you're looking at that sign, you're like, ooh, I'm thinking we're looking around. We've probably exceeded the weight limit, but what do they end up having in place there to kind of, that's not a problem. Do you know what that's called? They call it a safety factor. Okay. So when an elevator, for instance, is designed, they're going to actually design it not for the capacity that's posted in the elevator, but probably for about 5 to 8 times more than what actually is posted. Okay. So that in the event it does go over, there's not going to be a problem. So here, if this goes over the capacity, they're probably also gonna think about, okay, what is the safety factor? Those are things that we talk about, because I heard earlier, what do we learn in strength of materials? Those are the things that we look for in strength of materials. In statics, we define what are the forces in those cables, but then why do we want to know that? Well, so we can get the appropriate size and that we can also be safe about our design. Okay. So anyway, so a typical problem here is going to be, now let's make a diagram of that. Well, what does that look like? Well, over here, down on the left-hand side here, here's your free body diagram. We don't see the truck or the people pulling the cables, or we don't see the pulleys. We simplify our diagram and we really bring it down to, okay, what are the forces acting on each one of those cables? And then we represent those with the vectors and the labels that we see there. Okay, so we're going to be seeing that. Another thing that's going to come up when we are coming across metric problems. In the metric system, their standard way of expressing weight is actually to give the mass. So they will weigh something and it's going to be in kilograms, in grams. And so in the metric system, if you are given, you know, the mass of an item, in order to represent it as a vector, you have to change it to force units. And to do that, you are going to simply multiply by gravity. Okay. So when you get mass, for instance, 75 kilograms here, we're going to multiply it by 9.8 or 9.81 meters per second squared. And when kilograms times meters per second squared combines, it becomes a Newton. That's what that capital N there is. Okay. We'll talk about that more as that comes up, because you're going to see those as units in metric problems. Kilograms is going to be very common that it's there, because that's what they use most often. Okay. They don't use the Newton all that much. When they weigh something, they express it in kilograms. In the United States, when we weigh something, we express it in pounds, right? Those are that's a force unit. Do you guys know what the units for mass are in the United States? It is a slug, Jack. Good job. Yes, a slug. Who knew? I mean, we never use it, right? We never use it. We only use force. So in the English system, when we're doing problems, you're going to see pounds, most common, but you're also going to see kips. Kips is a kilopound. All right. So instead of saying 1,000 pounds, we're going to say 1 kip. All right. So that'll come up here and there with problems that we have. So, so just so that you know. All right. So equations of equilibrium. Let's jump into doing a problem, because I think it makes more sense when we can kind of apply this stuff. It's hard to talk about it and point at stuff as opposed to let's just jump in. So this is going to be the first sample problem we're going to do. You're going to want to put this into your notes for your practice problems. And what we're going to do is we're going to be solving this using the rectangular component method. All 3 of our practice problems are going to be that, and all of the problems that you're assigned are going to be that as well. So you'll notice here that as we you know, look at what's going on here, they are using the sine law. We are not going to do that. Okay. So again, I know there are multiple ways of solving things, but we're going to get good and we're going to utilize the rectangular component method right now, because again, that's going to be the most popular going forward. And it's usually the one that most people like to use. So we're going to start up here. And what we have is we have a ship unloading operation, and it's got a car that it's lifting or unloading, and the car is 3,500 pounds. Okay. And it's being supported by a cable going up. Okay. Right here from the ship. And then there's a worker who has a rope, and the worker is pulling that car over. Okay. What they want us to do at this moment in time, they want us to determine what is the tension in the rope that that person is holding onto, and also what is the tension, what is the force that the cable has to support with. Okay. So we need to draw a free body diagram. Okay. Let me get out I want to get out a straight edge here. Just so that, oops, a little better. If I have it. Oh, here it is. Got it. Got it. So I'm going to start by drawing my X and Y axis, and it's going to be going through the center of point A. I'm picking point A because point A is the point at which everything is coming together. I panicked. Oh, what? Wait, what? Sorry, my bad. Oh, all right. Yeah, we heard you. I think it was that you, John. And that's okay. That's all right. No worries. Okay, so we're going to draw an X and Y axis, and A is going to be at the center. Kiefer, we're on page 41, and we're looking at sample problem 2.4.
Sounds good. Thank you.
You're welcome. All right, so I'm going to draw a nice big, and this is going to be also, just so you know, Kiefer, this is our first practice problem that we're looking at, okay? In this section, and we're in we started module 3. All right, so I've got an X and Y axis. The center of this is going to be A. I'm not going to place A here right now because we're going to have some things coming from there, and I'll just probably interfere with it anyway. So I'm going to call this sample prob 2.4. Okay, now something that's going to be essential for all of our problems going forward, is that we need to put in our convention. Okay, so we kind of touched on it in module 2, but now it's official. We are using our convention in our upper right-hand corner for all of our problems going forward. This tells us what's going to be positive going to in the X and Y direction. So when we write our equations of equilibrium, we're going to know, okay, anything that we have pointing to the right, that's going to be identified as positive. Anything going to the left is going to be identified as negative. Okay. Now we've got our axis system. We know this is our positive X, our positive Y. We'll bring back our illustration and look at what we're going to do here. So here's our point A. So we're going to have our X and Y axis going right through the center here. Okay. So a known value that we have is going to be the weight of that car. So coming from point A, we would represent the weight of the car going straight down and then label it 3,500 pounds. Okay. So coming straight down from point A, I'm going to kind of darken this in. I am going to have, I'm not going to even call it a variable. It's just 3,500 pounds. 3,500 pounds. Okay. The next thing that I'm going to add, as I look here, I'm going to add the rope that the person is pulling over with. Okay. And all we're going to do is we're going to represent that it's going to be a force, but we're just going to draw the line right now. That's going to be 30 degrees. Okay. Just draw a line that's 30 degrees from horizontal going down and to the right. Now we don't know how long this is going to be. All right. Because that's going to be a value we have to solve for, but we need to represent it. And it's going to be a force that's going to be pulling away because he's literally pulling in that direction, right? On that rope. And we know this angle to be 30 degrees. And then the last item that we need to add is going to be this cable right here. Okay. So as we look at this, you're gonna notice that it's 2 degrees from vertical here. So do you see how the 2 degrees would be here with our vertical? Okay, so so we're gonna place that kind of steep like this, okay? And that's gonna be 2 degrees. Now here as well, because this cable, if this cable would be completely vertical, it would be going up, right? So because it has to have a vertical component, if you would, this cable will be supporting in this direction, okay? Now, what are we gonna call these? As you can see, they have some labels. They have A here in the middle, which is gonna be our origin, but they've got B up here on that crane or that cable. So I'm just gonna call this simply force B. And then we have C, where the man is pulling on our rope. So we're gonna call that C, all right? Now, sometimes there might not be letters, but you're gonna have to call each one of your vectors something, okay? Do not call it X, don't call it Y, don't call it Z, okay? Really kind of, those are off limits, right? Because those are for something else. Those are axes identifiers. But A, B, C, F, P, Qs, I mean, those we see a lot, okay? You'll notice that in the example here, they chose to call it capital T, and then they said AB, and then capital T, AC. That's fine. I just feel like it's kind of long. So I'm just saying, really is arbitrary. I'm just gonna call it force B. That way I've got a BX and a BY, rather than a TABX and a TABY, just to kind of keep it simple. All right, so now that I have these forces here, and you can see my 2 unknowns are gonna be my B and my C. What do you think the next thing I need to do is? I heard components, right? Let's draw our components in place, right? Anything that is not on the X and Y axis already, because we know we're gonna do the rectangular component method, we wanna get rectangular components for. So the first one, I'm just gonna, through my endpoint of C, I'm gonna lightly kind of put construction lines here, or you can put dotted lines. And I'm gonna identify my X. Make sure that you're going over. If you're doing, and this is something just to pay attention to details, remember, I'm not asking for perfection on your diagrams. Mine certainly are not. But if you have an X component, line it up with the end of that vector. Does that make sense? Right? Then it's easy to see. If you just kind of randomly put an X and it's past it or not all the way over there, take time to put those little details in, please. Okay. It is important. You might not think, oh, it's no big deal. It kind of is, because remember, yeah, I mean, I know it's for me and it's for, school right now, but get in the practice of making good diagrams that are easy to follow, because as you get out in industry, you're going to have to share your work and prove, how you did something. And you're going to be sharing that with other people, and they're going to have to follow it. So, so it is important to get in that habit. So this is going to be my, which side do I want to put this on? CY. Then I'm doing this very same thing for my B, X, and BY. And you know what? It doesn't really take that long to do that. And if you know that you're, not great at straight lines, get a little straight edge, right? Or a scale. I know I'm not great at them. I'm okay at straight lines, but I'm not great at them. Right. Anything else as I'm looking at my diagram? Do I have everything labeled, angles? I don't have any X's or Y's floating. They're all in the X and Y axis. Everything has arrowheads. Okay. All right, what's next? Yeah, let's solve the components and see what we've got here. So, so I'm going to call this step number 1. We're going to call it free body diagram, FBD. Okay. And then step number 2 is going to be components. Okay, now components again are going to be any forces that aren't already on the X and Y axis. So our 3,500, it's on the Y axis. You wouldn't say that's at a 0x component and it's all in the Y. Just don't even include it here because we'll include it in our equation of equilibrium later on in the Y direction. So we're just doing components of what's here. So BX, BY, CX, CY. So let's look at our BX, okay? Our BX right now, it's going to be our horizontal. And you'll notice that we're given our 2 degrees here, right? Using original information, and it's always good to do that, all right? It would mean that my X component is an equivalent length out here. Again, do not put your X component labeled up on the top here. We need it at the place of application. That's really critical. All right. You might, and again, you might not think it is, but it is. Because later on, when we have forces that are going to be along a line, I've got to know that where the X component is. I got to know it, all right? Because it's gonna cause rotations and they're not floating, all right, away from the body. Equivalent length out here. So if I look at my 2 degrees, it would be the side opposite, right, over the hypotenuse. So I'm going to say my BX is going to be equal to the sine of 2 degrees times B, okay, times B. Does that make sense to everybody? So now, I know I can't solve this for an actual number, but what I can do is I can get the sine 2 degrees into a decimal. So 2 sine. And what you want to do here is you want to hold at least 4 decimal places. So I'm getting 0.0349, and then it's going to be times B. Okay. So we're going to put this component in terms of its hypotenuse or in terms of its force. So that's going to be that. And then over on the other side here, just what I always do, I'm going to put my y's over on the right. So by then, it's going to be equal to, so by, oopsie, by is here. So that's going to be the side adjacent over the hypotenuse. So this is going to be the cosine because of the position of that 2 degrees. Don't get too comfortable that your cosines are your x's and your sines are your y's. They're gonna throw some of these in here. So watch for that. So cosine of 2 degrees times B. So 2 cosine, my by is going to be equal to 0.9994 B. And again, don't round at this level because we're going to be using these, and that way round your final answer. So 5 decimal places is what you want to do. Okay, go ahead and solve for your components at C. I'll just sit here and I'll put mine in. I'm not going to talk it through. And then we can compare. So as you're kind of finishing that one up, you should be getting 0.866 times C, because that's the cosine of 30. And you should get 0.5 times C, because that's the sine of 30. Okay. That one was in our standard place. Okay. So now the next thing that we're going to do is we are going to implement our equations of equilibrium. Okay. So step number 3 is going to be, I just call it equations of equilibrium. Well, I is in there. Oh, well. Challenge today. Okay, equations of equilibrium. We've got 2 of them. Our 2 equations of equilibrium are going to be our sum of our forces in our X equals 0 and the sum of our forces in the Y equals 0. Okay. So we're going to start with the sum of the forces in the X equals 0. You have to write it just like that. There is no other version that you can do. You have to show the summation symbol, capital sigma, I believe. Capital F means I'm summing forces, okay? Capital F in the X direction, sub X is equal to 0. This is an equation of equilibrium. There's an equal sign, there's a left side, there's a right side. Has to be. I feel like I'm shouting at this point. So it's kind of important. And it's probably something that, you know, you got to do, all right? So make sure that you do that. It's like announcing to me, it's telling me, this is what I'm gonna do. It's a variable, it's a equation in variable form before I start plugging my numbers in. Now, as we look at this equation of equilibrium, the left side says that's where I'm gonna do my summation, okay? So what I'm gonna do is, I am gonna look up here on the left-hand side, I'm gonna say, okay, just on the x-axis here, what do I got? I've got two forces with arrowheads, right? I've got a BX and I've got a CX. This is left-hand side so far. Now, according to my convention that I have up in the upper right-hand corner that's required, what is the sign I'm going to put in front of my B? A negative, right? It's going to the left. Yes, so negative. And what is the sign I'm going to put in front of my C? My CX? A plus, yes, it's going to the right, right? That's why I need arrowheads on these things. That's what tells me the sign. Do not put positives and negatives in your components here. Don't do it. Leave those as absolute values. You might come up with a negative value. Doesn't matter. Don't do it. Resist the urge, okay? Because down here is where we're going to get those positives and negatives, okay? And sometimes if students are putting the negatives up in here and they get down here and they get a negative value, they'll take a negative times a negative and they'll make it positive. No. Okay. Just absolute values up here. And then we'll add and subtract based on their direction in the equations for equilibrium. Okay. Now, is that everything on the x-axis? Yeah, there's nothing else. So sometimes this is going to be 2 forces. Sometimes this is going to be 8 forces. All right. It just depends on what we have going on. So right now, the left-hand side is satisfied. I summed my forces in the X direction. Equation of equilibrium. So I'm going to go like this, equal to 0. You have to do that. This is an equation of equilibrium. It needs an equal sign. It needs 2 sides at all phases of the problem. If you don't do this, I take points off. You might say ticky-tack. It's not. It's an equation of equilibrium. All right. Now, I'm going to fill in how my values from up here. So I'm going to now say, all right, for my BX, I'm going to substitute the value up here. So I'm going to say negative 0.0349B plus 0.8660C, okay, is equal to 0. Now I have 2 unknown variables, 1 equation. I know I can't solve it, but what can I do here? I can do one more thing. I'm a very positive person. I try to be positive. What do I want to do? I want to get rid of that negative sign, right? Let's get rid of that negative sign and put it on the other side. So I'm going to say 0.8660C is going to be equal to 0.0349B. All right. Now, I'm stuck here now. I can't go any further. But I have another equation of equilibrium, don't I? Yeah, I do. So I'm going to put that other equation right next to it. That other equation is sum of the forces in the y direction equals 0. Okay. So now I'm going to go look back up at my diagram. And I'm going to notice that I have a BY, I have a CY, and I have a 3,500 pounds. Okay. So I'm going to put BY, CY, and 3,500 pounds. Make sure the units are in there. And before I go to the other side of the equation, put the signs in front of each one of those values that you think it's going to be. Put a sign in front of the BY, in front of the CY, and in front of the 3,500 pounds. the sign that goes in front is going to be according to my convention. So anything going up, BY, it's the only one going up, is going to have a positive in front of it. And anything going down, CY and 3,500 is going to have a negative sign in front of it, right? Okay. So I'm going to have a positive, negative, negative. Okay. So am I done with that line? No. No. What do I need to add? I shouted it before. Very important. Equal to 0. Exactly. Equal to 0. Now I have an equation of equilibrium. All right. Now here again, we're going to substitute the values that we solved for up on top. So we know that BY was 0.9994B minus CY was 0.5C. And then you'll notice that I can't combine my 3,500 with anything on the left-hand side right now. So what I'm going to do is I'm going to move it to the right-hand side right away. And I'm going to say equal to, and it becomes positive, right? 3,500 pounds. Notice my force of 3,500 pounds has units in all phases. So it has it in this line. It has it in this line. We're going to continue to carry it through. That's required. I don't want these units to magically appear at the end. Okay. Because, it's not what we're going to do. There's going to be times, especially when you get into other classes, strength of materials, you got to put the units in to be sure that you resolved it correctly. You're going to have cancellations and combinations. Okay. So here, can I solve this equation? Not yet. By itself, I've got two unknowns, but what do I have over here? I've got another equation with the same two unknowns. Aren't you excited? We can now solve this. I was kind of sad when this was here. I was kind of sad when I looked there, like, oh crap, I can't do this. It's only going to stop. But now I've got two equations with the same two unknowns. And all of a sudden, the light goes on. So by substitution method, we are going to solve for B and C using two equations, two unknowns. Okay. All right. So I am going to kind of keep this right here. And I am going to go to step number 4. This is going to be my two equations, two unknowns. Okay. And I'm going to identify my equation number 1, and I'm simply going to use the sum of the forces in the x equals 0, 1. So 0.866C is equal to 0.0349B. That's going to be my equation number 1. My equation number 2 is going to be the sum of the forces in the y equation, which is 0.9994B minus 0.5C is equal to 3,500 pounds. Make sure you keep that in there. Okay. And you can use LB for the pounds, or you can use the symbol. I tend to default to the symbol because I think I've mentioned this before. Sometimes that LB can look like a 1, that L can look like a 1 to me, and then I accidentally stick it in there. So. Right. Yeah. Yeah. Oh yeah, exactly. Yeah. Yeah. If you do B's like this, and some people do, right? And LB can look like a 16. So yeah, I use the symbols just to kind of help me with that. Okay. So now the first step is going to be picking one of the equations and putting one of the variables in terms of the other. So which equation do we want to deal with? I always try to do myself a favor, and it feels like when there's less variables to deal with, that's the one I want to do. So I'm going to start with number 1, and I'm going to put C in terms of B. So I want to get C by itself on the left-hand side, right? I'm going to kind of get rid of this now. So I am going to, my step number 1 here, if you would, in this step number 4 is going to be, I'm going to rewrite this. This is going to be my equation number 1, 0.866C is equal to 0.0349B. And I'm going to divide both sides by 0.866. So C is going to be equal to, and check my work here because I'm 0.866 divide. I'm getting 0.0403B. All right, I'm just kind of doing these along with you, and we don't have the answer key in front of us because the book took a different approach. But we will end up with the same final answer. Did you guys get 0.0403 C or B? I'm sorry, B. So now what we have is we have C in terms of B, or C by itself on the left-hand side. So now I'm going to, since I used equation number 1 here, I'm gonna flip to equation number 2. Okay, and this is kind of like step number 2 here. And I'm gonna rewrite this over. So 0.9994B minus 0.5 times. Now, instead of writing C here, I'm going to write 0.0403B. Okay. Because that's what C is equal to. And then I'm going to set that equal to 3,500 pounds. So now I can multiply this out, right? And then I can combine my B's, because notice I only have one unknown variable here. So I'm going to have 0.9994B minus 0.0202B. Is that right? Okay. Is equal to 3,500 pounds. Now I can combine these two, right? So 0.9994 minus 0.0202, 0.9792B is equal to 3,500 pounds. Notice I'm putting my units in every single line. Solving for B, 0.9792, divide on both sides. B is equal to so you should get, once you got it all plugged in, 3574.3. Okay. Everybody get that? Now let's peek at their answer. Okay, so this is going to be their answer for the tension in AB. And if we look here, you're going to notice that the book gets 3570. Are we wrong? No. What does the book do? They round to 3 significant digits for their last. So they're correct. I mean, when you round to 3 significant digits, yes, that's the number. And if we would round ours to 3 significant digits, we would get the very same number. Okay. So you are fine, just so that you know. And I always carry all the way through. So if you check a final answer, that doesn't mean you even have to put it in their final form, but just make sure that yours is within that rounding to 3 significant digits. Okay. And you'll be fine. I'm always going to put in the answers for the final answers for the problems for you that the book uses. And I'll do that because of exactly that. They're consistent with 3 significant digits. I'm not, because then I don't want you guys to fret over a decimal or 2 or anything like that. Okay. All right, we've got B, but we still need to find C. So now, since we solved for B here in equation number 2, we're going to substitute B back up into equation number 1. Now remember, right here in this step, equation number 1, we solved for C in terms of B. We're actually going to put it in right there. Okay, right there. So my third step here is going to be taking that equation. This is going to be equation number 1. C is equal to 0.0403 times 3574.3 pounds, units in there. Okay. And my C is equal to 144 pounds, 0.046. And that's what they get to, 144 pounds. Box around your final answer with the units. And again, I better see the units in here because I don't want them to magically appear like, oh yeah, I was supposed to put those in. Okay. Even if you put the right units in the very end, but you didn't include them in the other parts of the problem. Remember, I actually am more interested in how you're solving these problems because that lets me know, I mean, this is a long process. It's a kind of a big deal, okay? So, so if a calculator issue happens at the very end, or sometimes what can happen is maybe you just put the angle in the wrong spot, but the rest of everything else, it affected everything else and your numbers didn't come out, but your whole other process was like spot on. You're getting like almost all the points, okay? So that's why I want to be able to do that for you. And it then lets me kind of in on, you know, if you're not getting the right answer, how come, okay? If it's just a little error like that, that does not concern me because that happens to all of us. But if it's, you know, if it's, you know, in the process or we're skipping something and then we want to get some more practice and maybe have a conversation or sit down and look at it together. Okay. So let's review our process. Whenever we're doing these problems, rectangular component method, it means we're going to be breaking things into our X and Y components. So number one, we're going to draw a free body diagram. We're going to add all of our knowns, our unknowns, and then any forces that are not already on the X and Y axis, we're going to put them on there and we're going to label them. And each one of those forces are going to have an arrowhead. Additionally, we're going to make sure that we have our convention in the upper right-hand corner. Once we have that in place, we're ready to solve for our components. Now, in this case, we didn't have numbers for, if you would, the resultant forces of B and C. So we had to put each one of those components in terms of their hypotenuse. Okay. Now, why did we do that? I now I can kind of explain why we did it. Now, after we've got our components, we're going to go down and we're going to use the equations of equilibrium to help us solve for our unknown variables. Now, if we would leave, so let's cover up our second line here. If we would have left Bx and By just like that, do I have two equations with the same two unknowns? No. That's why we needed to put each one of those in terms of their hypotenuse so that now I have the same two unknowns in each one of those equations. Okay, that's where it is. That's where it is. That's why we do that. So I sum my I sum my forces in the X equals 0. I sum the forces in the Y. Remember, you have to tell me what you're doing. You have to announce it to me, your equation in variable form. Sum the forces in the X equals 0 before we do anything else. And it is not sum the X equals 0. It is not sum F equals 0. It is not Fx equals 0. It's sum, the symbol, capital F, sub X equal to 0. I know I'm emphasizing that a lot, but it's for a reason. 24 years of teaching. I know. And this will make sure that you get it. Same thing for the Y. Tell me what you're going to do. You have the summation symbol F Y equal to 0. No other options, because this is the only way you're going to see it. You're going to see it in every textbook that does statics. They're going to show it in that way. That's a standard form. Okay. And then down below, you're going to put your variables in. Your signs are going to be dictated by the convention and the direction of the arrows. Okay. And then you're going to get as far as you can. And when you get to a point where you're like, I can't go any further, I've got two unknowns in this equation, then you start looking at, all right, substitution method, and then making sure that you're following that along. Okay. And then also keeping your units in all phases of the problem. All right. Questions on our first sample problem 2.4. Okay. So then what I'm going to do is I'm going to stop recording right now.